Number 10 from the worksheet, you have one oligopeptide, alanine, proline, cysteine, lysine, and arginine. For part A, it asks you how many moles of sodium hydroxide would be required to titrate 1 mole of fully protonated form to its fully unprotonated form. So for sodium hydroxide, in this case, it would give you hydroxide ion. So hydroxide ion will take out the proton from the fully protonated form in order to become the fully unprotonated form. So to find the amount of the hydroxide ion that we need in this case, you have to look at the oligopeptide structure and look for the group or the side chains that can deprotonate for proton. So we first begin with alanine. So alanine, because it's at the N terminus, the structure of alanine would contain N terminus and because alanine doesn't have any side chain, so the first group that can deprotonate here is the N terminus of the side chains. Sorry, the N terminus of the alanine. So proline doesn't have side chain either, so we skip proline. And then cysteine, there's a side chain group that can deprotonate. It is a SH group here. And then for lysine, the side chain of lysine can also deprotonate. And the form will be in NH3 plus. And for the last one, our arginine. So arginine contains two groups that can deprotonate. The first one is the C terminus of the oligopeptide, and the second one is the NH2 plus from the side chain. So for the fully unprotonated form, it will be resolved at I diagram here. So it will lose one proton for each group here. So you can see that the total of the number of proton between the fully protonated form and fully unprotonated form is 5 proton. So so 1 mole of oligopeptide would require 5 moles of hydroxide ion in order to titrate and make it become the fully unprotonated form here. Part B is asks you to calculate the pH of the solution that contain only fully unprotonated form of this oligopeptide. So fully unprotonated form, what is that? So this is the weak base, because we already taught that we already learned from class that strong base would only be sodium hydroxide or potassium hydroxide, etc. But so any of the oligopeptide or any amino acid is considered weak if you have fully protonated peptide or fully protonated amino acid. It would consider to be a weak acid, right? So its fully unprotonated form would be considered as a weak base here. To calculate the pH for the weak base, what or which equation will you use? So there's only one equation that you need to think about, is that using the Kb to calculate for the concentration of hydroxide, and then we're gonna use POH equal minus log concentration of hydroxide, and then change POH into pH. Let's take a look of the pKa value of each of these group that can be protonated here. I've listed the pKa of the side chain of cysteine, lysine, and arginine already, but what about the pKa of the N terminus of the alanine here? So this N terminus is actually the N terminus of oligopeptide, right? So the pKa of N terminus of the oligopeptide would be 7.4. Why the C terminus of the oligopeptide would be 3.6. Keep in mind that the value of pKa of the N terminus and C terminus of oligopeptide are different from the pKa of the N terminus and C terminus of just the single amino acid. So for single amino acid, the N terminus would be 9.6 and C terminus would be 2.1, but it doesn't apply in the oligopeptide pKa value. So make sure that you know about this difference here. To calculate the pH of the weak base, we already mentioned that you need to use the Kb. So the equation that you use would be Kb equal to x squared divided by the initial concentration of this oligopeptide. So in this case, it would be 1 minus x, right? But we know that x here can be discarded in the denominator form. So Kb here would be equal x squared divided by 1 molar. So the problem is which Kb value should we plug into these equations? Starting from fully deprotonated form, if this fully deprotonated form is in water, so it will give you one hydroxide ion, and then it will becoming the second least fully deprotonated form. From this equation, you can notice that the difference in the number of proton of fully deprotonated form and the second least deprotonated form is only 1 proton. So you would think about which will be the first group of this oligopeptide that can receive proton from water. So the answer is that it would be the group that has the highest pKa, because if you got the highest pKa, you would be the first one to grab the proton from water. So in this case, the highest pKa of this oligopeptide here would fall into the pKa of the side chains of the arginine. So this pKa for this reaction would be 12.5. So you can use the ICE table to look at the constant of Kb, and then you get Kb equal x squared divided by 1 minus x. But since we know that the x amount here is very, very minimal, so we can discard it in the denominator. So the next step is to solve for x. So since we know that the pK of this step is equal 12.5. So you have to change pKa into pKb and then change pKb back into Kb. So Kb in this case would be equal 0.0316, and you can plug into this equation here. So you solve for x, and x will be 0.177. So this x is actually the concentration of hydroxide ion, right? So you can calculate the pH of this solution by first calculate the pH equal minus log concentration of hydroxide, and then calculate for pH using 14 minus pOH. So the answer for this question, your pH would be equal 13.25.